Hello and welcome to the Harvard Radcliffe Institute. My name is Claudia Rizzini. I'm the Executive Director of the Fellowship Program. The Institute is one of the world's leading centers for interdisciplinary exploration. We bring students, scholars, artists, and practitioners together to pursue curiosity-driven research, expand human understanding, and grapple with questions that demand insights from across disciplines. You can be a part of this vibrant community by attending public programs such as this one, visiting virtual exhibitions, or pursuing the special collections held at the Schlesinger Library. To learn more, you can visit radcliffe.harvard.edu and sign up to receive more information on news and events. We'll begin the program with a presentation by Joan Najita. After the presentation, the speaker will respond to questions from the audience. Please use the Q&A feature on Zoom to submit your questions at any time throughout the program. We ask that you keep your questions brief to allow us to address as many as possible in the time that we have together. It is my pleasure to introduce Edward, Francis, and Shirley B. Daniels Fellow Joan R. Najita. Dr. Najita is an astronomer at the NOIR Lab, the National Science Foundation Center for Ground-Based Optical and Infrared Astronomy. At NOIR Lab, she develops research resources for US astronomers and also carries out research. Her research goal centers on understanding how stars form from interstellar clouds and how disks surrounding young stars create planets and the chemical ingredients of life. Dr. Najita has pioneered the development of innovative techniques to probe planet formation environments, including infrared molecular spectroscopy of disks, thermochemical models of disk atmospheres, and more recently, the synthesis of diverse datasets. With a lifelong interest in the power of science to inspire and in the role of science in society, she's actively engaged in communicating science to the public. While at Radcliffe, Dr. Najita is using data and theory to examine the diversity of planetary systems and the reasons for their diversity. Planets beyond our solar system absorbs our imagination and offer insights into our own origin and place in the universe. While it is now known that planets commonly orbit other stars, their system architectures vary significantly from our own. Their architectures and histories raise questions about how our own solar system formed and offer the opportunity to understand how and why our planetary system is similar or different from those around other stars. Dr. Najita credits her passion for astronomy to a chance visit by a planetary scientist to her high school in Honolulu, Hawaii. She was captured by the images of Jupiter from the Voyager spacecraft and the realization you could get paid to study such images and investigate distant worlds. Following this discovery, Dr. Najita received her BA in Physics and Astronomy and Astrophysics at Harvard and Radcliffe Colleges, graduating summa cum laude. She went on to earn her MA and PhD in Astronomy from the University of California, Berkeley. She is a recipient of the Zonta Amelia Earhart Award and the Annie Jam Cannon Prize for Early Career Research in Astronomy. She is also a fellow of the Guggenheim Memorial Foundation and the American Association for the Advancement of Science. And now it is my pleasure to give the virtual floor to Joan Najita.
Thank you, Claudia, for that incredibly kind introduction. I'm trying to share my screen. So thanks again, Claudia, for that wonderful introduction, much too kind. I want to thank all the funders of the Radcliffe Institute and the Radcliffe Fellowship Program, and especially Shirley B. Daniels for making this fellowship year possible. And heartfelt thanks also to all the Radcliffe staff and all my fellow fellows for making the Institute such a welcoming, stimulating, and truly unique place to be. Hello, I'm Joan Najita from NSF's NOIR Lab, and today I wanted to share a little about the project that I'm working on this year on the diversity and origins of planetary systems. But before beginning, I wanted to spend just a moment talking about my organization that I work for, since it's probably unfamiliar to many. As Claudia mentioned, NSF's NOIR Lab is the National Science Foundation's Center for Optical and Infrared Astronomy. We're based in Tucson, Arizona, and we develop and operate telescopes in Hawaii, Chile, and Arizona, including the Kitt Peak National Observatory shown here. In addition, we also create and serve data sets, including tools that can be used to analyze those data sets. And this is all in the service of the idea that anyone with a good idea should be able to pursue that idea using forefront research capabilities. And if you're interested in exploring the universe as well, I invite you to visit www.legacysurvey.org, where you can explore one of the recently created data sets and see what's going on in the Milky Way galaxy, our home galaxy, as well as galaxies beyond the Milky Way out there in the universe. But to return to the topic of my fellowship program on the diversity and origins of planetary systems, to introduce that idea, I wanted to begin by describing the classic picture of planet formation, the picture that we developed to explain the planets in our own solar system, then go on to describe some of the diversity in the planets that have been discovered beyond the solar system, what new insights they provide, and give examples of some of the open questions that astronomers are dealing with. Then, if time allows, I'd also like to spend a couple minutes talking about a different kind of diversity in astronomy, the diversity in how discoveries are made and the implications for the development of our field and for interaction with society. So beginning now with the classic picture of planet formation, which was designed to explain the planets in our own solar system. These planets, as you well know, are the inner solar system planets, the terrestrial planets, Mercury, Venus, Earth, and Mars, and the giant planets, Jupiter, Saturn, Uranus, and Neptune. And some of the questions that we have about the planets are, how were they made? Where did they come from? And whether the solar system is unusual or not, and why. We can get a big clue to the origin of the solar system by simply looking at where the planets are in the night sky. On a given night, we'll see that the planets really are stretched out in a line on the sky, really a plane in three-dimensional space. And so here in this image, we have Mercury, Venus, Saturn, Mars, the Moon, and Jupiter all in a line, a plane in three-dimensional space. There's also some stars. And so seeing that the planets are in a plane, it's perhaps not too hard to imagine that they formed in a flattened disk of gas and dust. By gas, we mean mostly hydrogen and helium. And by dust, we mean not household dust, but small grains of that are made out of ices like water ice, carbonaceous soots, and silicate ash. Now you might be wondering, where can I find an example of a flattened disk of gas and dust that might be making a planetary system? Well, you might have seen a planet formation environment, perhaps on a calendar or a mug or a mouse pad, because these images of planet formation environments are very popular in astronomy. Here's an example of a planet formation environment that was captured by the Hubble Space Telescope, the famous pillars of creation in the Eagle Nebula. And deep inside these dark pillars are examples of these planet-forming disks. Another example is this popular calendar image of the Horsehead Nebula in Orion, and deep in these dark regions here are also examples of planet-forming disks. So the question for planet formation is, how do we go from these flattened disks of gas and dust to make the planets that we know of? And the explanation that we astronomers have come up with is an amazing tale extending over orders of magnitude. And the story goes a little bit like this. So we start with the smallest things in the solar system, micron-sized bits of dust that collide and stick and grow to make pebbles about a centimeter in size. These pebbles get themselves together to make kilometer-sized planetesimals, If these planetesimals are icy and they see the star, they burst into these comet-type shapes. But if they're not particularly icy, they look like asteroids. These kilometer-sized objects collide and grow to make protoplanets the size of Mars or the Moon. And these protoplanets then collide and grow to make the Earth. We can keep going with Earth-sized objects colliding and growing to build giant planet cores, maybe 5 to 10 times the mass of the Earth. And if these cores grow quickly enough, they can begin to enrobe themselves in a little bit of the gas that's in the nebula, in the disk. And if they grab a little bit of gas, then they would end up like an ice giant like Neptune. But if they grab a lot, then they can end up as a giant planet like Jupiter. So this picture of planet formation, which is called core accretion, because we start with a core and then we accrete a gaseous envelope. That picture is very popular and very enduring because it explains a lot of things about the solar system. It explains why we have both terrestrial planets and giant planets in the same system. But now let's look and see at some of the new planets that have been discovered and see how our picture does there. So let's begin by looking at some of the planets that have been discovered very close to their central stars, say within the orbit of Jupiter. These planets have been discovered with a couple of different methods, the first being the radial velocity method. So in this method, we have a star and a planet going around it. We don't really see the planet, but the planet exerts a gravitational pull on the star. So as the planet orbits, the star exerts its own little wobble, and through the motion of the star, we can infer both the mass of the planet and how far away the planet is from the star. Those kinds of observations might be made with a ground-based telescope like the Wind Telescope at Kitt Peak. So from these observations, we can infer the mass of the planet and its separation from the star. And we can also use other methods to make similar kinds of observations. For example, we have the transit method, where we have a star and a planet passes in front of the star, and the planet is darker than the star, so it blocks out some of the light from the star. And by looking at the decrement in how much fainter the star gets as the planet passes in front of it, we can infer the size of the planet. And by watching it go around a couple times, we can infer the orbital period and therefore the distance of the planet from the star. And these kinds of observations could be made both from the ground, but also have been made a lot with space telescopes like the Kepler Space Telescope. So now we're in business. We've measured some planet masses and some planet sizes and their orbital separations from the star. So we can make a plot. So let's plot the mass of planets that have been discovered versus the distances from their central star. And here for reference, we have the position of Earth, Jupiter, and Neptune. And let's see where the new planets that have been discovered end up. Well, they end up there. So this shows that planets beyond the solar system can be much more massive than Jupiter in our own solar system. Planets can be much closer to their central stars than the planets in our solar system. And they can have some pretty unusual masses. So for example, this group of planets, which have masses between Earth and Neptune, are extremely common, but have no counterpart in our own solar system. So these results probably raise a bunch of questions in your mind. And one of those questions would be, why are these planets so close to their central stars? That's pretty different from the solar system. Well, astronomers, we like to start with what we know or what we think we know. And so our current working hypothesis is that planets formed kind of where we thought they did in the core accretion picture at these larger distances, and various processes have been at work to move them in closer to where we see them today. But this leaves open many questions. Why are some planets so much more massive than the planets in our solar system? Why are the planets so much closer? When did these planets form? When did they migrate? And why did they stop? These are all open questions that astronomers are working with. But these observations also raise other questions about the likelihood of habitable planets and our understanding of how the Earth formed. Because these observations, the transit observations, suggest that perhaps something like 20% of stars like the Sun have an Earth-sized or Venus-sized planet at an Earth-sized or Venus-like distance from the central star. Now, if you're interested in knowing whether the solar systems like ours are common or not, or if there are habitable planets out there, then starting with a population that's like 20% that potentially are in that category is pretty interesting. But I wonder whether we really understand what we discovered here, because this high fraction of stars with these kinds of planets seem to be in tension with our classic picture of how planets like Earth formed. So let's think back to the picture of core accretion that we were just discussing, where we were forming the Earth and thinking about how that picture goes. It's actually quite a violent story, because in order to go from these Mars-sized objects to an Earth-sized planet, which is 10 times more massive, basically we have to smack a bunch of 8 or 9 or 10 Marses together in order to get an Earth. Each of those collisions is quite catastrophic and is expected to eject a small fraction, but a significant, small but significant fraction of the planet out into the inner solar system and to create a lot of debris. In other words, in these collisions, a piece of the planet comes off, it's ground into very tiny dust again, and producing a hot ring of dust as that material is heated and illuminated by the central star. Now, if you take a small portion of a planet and you grind it down to fine dust, it ends up taking up has a huge emitting area, much larger than a single planet. And so this hot debris signature that's expected to result from the formation of Earth is expected to be one of the most visible signposts of Earth formation. And that's kind of the problem, because if 20% of stars like the Sun are forming Earths in the way that we've always thought that they form, 20% of stars should have this hot dust signature that should be really easy to detect. And the problem is that although this is the expectation, only a small fraction of stars really show this hot dust signature. So where are the dusty footprints of these forming Earths? This is clearly a tension between our expectations and the interpretation of observations. And so as I described in earlier work done with Scott Kenyon here at the Center for Astrophysics and Ben Bromley at the University of Utah, this tension potentially suggests either that theory is wrong or observations are wrong. Even though we love core accretion and it's been our guiding light all these years, perhaps some elements of that theory are not correct and Earths maybe don't really form this way. Or perhaps some of the observations are wrong. And while it's really exciting that 20% of stars like the Sun might have Earth kinds of planets, perhaps there really aren't as many out there as we really think. So trying to figure out both of these ideas are really exciting, and trying to figure out what the resolution might be is something that I hope to think about this year. So I hope this gives some of the flavor of the excitement over the planets that have been discovered close to their central stars, the questions they raise, the insights they offer, and how they challenge our understanding of planet formation and the origin of our solar system. But now let's have a look at some of the additional, even more recent results about potential planets at much larger distances from their central stars that have been introduced by observations made at much longer wavelengths. So these observations we were just talking about were made with optical observations at wavelengths that our eyes can see, but these measurements at much larger distances are made at radio wavelengths from images of planet formation environments. They mostly come from the Atacama Large Millimeter Array, or ALMA, which is located on the Chajnantor Plateau in Chile. And ALMA is a collection of many radio telescopes that, working together, can synthesize very high sensitivity, very high angular resolution observations of the universe. In other words, it can discern very fine structures. And when this powerful new facility decided to make its first high angular resolution observations, it chose to look at a planet-forming disk. And this is what it saw. Bright rings of luminous emission interleaved with dark gaps, nested rings of emission on the same size scale as the orbits of the planets in our solar system, but extending to much larger distances. Not only is this a beautiful image, but amazingly, it's exactly what astronomers expected to see. Because in the decades leading up to this observation, if you'd asked astronomers, what would a planet-forming disk look like? These are the kinds of pictures we would have drawn. A planet forms, and it clears out a dark gap in the vicinity of its orbit. And if you have multiple planets in the same system, you would end up with these multiple nested rings. And amazingly, that is exactly what we observed. So astronomers were very thrilled, and people have continued to make many such observations. And those observations all show the common element of these rings and gaps. So here are a bunch of rings. Sometimes the rings are very narrow, sometimes they're thicker, sometimes they're quite thick. And if you look closely, sometimes you can see very fine filigree spirals. But the main characteristic are these rings and gaps. And because these rings and gaps agree so closely with what astronomers have expected to see, people have rushed to try to figure out what kinds of planets could be causing them. And so we could put those new planets, potential planets, on our same plot. So here again are planet masses and the distances from their central stars. Here's Earth, Jupiter, and Neptune. These dark dots here are the planets we were looking at earlier, and these colored points are the locations of the new planets in this plot. So we have planets much more massive than Jupiter, extending down to Neptune masses and below, and also to much larger radii. Now this plot is on a logarithmic plot, so it kind of squashes all the distances together. So to give a clearer idea of what some of these results are, schematically, if these are the planets in our solar system, many of the rings are out here, and they may indicate the presence of planets between the rings. So planets at much larger radii than the planets in our own solar system, illustrating again how nature produces a lot more diversity than we imagined. But that's not the whole story. Because many of these disks, while the most popular ones are these large disks that have been studied, where people are trying to figure out whether they have planets, many of the other disks are much smaller. So this raises questions. First of all, whether any of these rings and gaps that we see really are the footprints of planets, but also what is the relation of any of these images to ourselves, to the solar system? In other words, in what kind of disk did the solar system form? And when we look at any of these images, are any of them an image of what the solar system might have looked like in its infancy? To answer a question like that, we can begin with a disk. We can take an image of a disk like this, evolve it in a computer, and look to see whether it ends up like the solar system. In other words, these images that we see are images of disks made out of pebbles and planetesimals. We could put those pebbles and planetesimals into a computer, let them jiggle around and create debris and grind themselves down. So this is an image at 1 million years. Let them grind themselves down over tens of millions of years to billions of years and see which ones end up like the solar system. That's a great idea, but we could do even better because it's clear that there are many different kinds of disks out there, and we should probably consider all those possibilities too. And in addition, rather than just letting stuff grind down and just waiting to see what happens, we could also make use of all the observations of debris that astronomers have been collecting of images of this grinding down process on these large super solar system size scales. In other words, Let's start with a bunch of different initial conditions, put them in a computer, let them grind down, and try to match all the properties of the debris that have been observed, the sizes of the debris, the brightnesses, and how often they occur, and try to figure out what evolutionary paths are possible in going from these initial conditions as disks evolve, and then ask which paths lead to the solar system. This is a project that I've also been working on with Scott Kenyon at the Center for Astrophysics and Ben Bromley at the University of Utah. And the result that seems to be emerging is of two distinct life histories of disks. Disks that are born big live spectacular lives. When they're young, 1 million years old, they have these beautiful rings and gaps. And as they age, they are the ones that produce all the debris that astronomers have been observing. They are the perennial favorites, the attention-grabbing stars of the show. The disks that are born small, though, they never do anything so demonstrative. They don't produce this kind of debris. And instead, they live tidier, quieter lives, eventually evolving to make the solar system. So these two kinds of disks, they present two different faces to the universe. To an interstellar traveler, perhaps equipped with infrared or radio eyes, the big disks would appear as spectacular tourist attractions. When they're young, they have the rings and the gaps, the filigree structures. But if you missed it in the first few million years, that's no problem. They remain spectacular throughout their lives for tens of millions of years to billions of years, like luminous neon signs inviting passersby to come in and take a closer look. In contrast, the smaller disks, they hardly even have a porch light on, and we'd be very tempted to just zoom past them on the interstellar highway. So these kinds of observations and these kinds of results give us some insights into our origins and give us some clues about where to go next. Because although these little disks don't appear to be particularly spectacular, they're likely to hold important clues to our origins and are certainly worth a closer look. So it'll be really exciting to see what astronomers find there. So I hope this conveys some of the excitement about the new populations that have been discovered of planets, the insights they provide, the questions they raise, and some of the methods that astronomers use to address those questions. It's truly an exciting time to be working on this topic, and I'm so fortunate and so grateful to have the opportunity to be at Radcliffe this year to think about these kinds of questions. But Radcliffe is also here to help us reckon with societal challenges and to improve the world. So in that context, I wanted to share a few additional thoughts about another kind of diversity in astronomy, the diversity in how discoveries are made and what that means for the way we interact with society and plan for the future. Now, this is a really major topic, and I can't possibly do it justice in 5 minutes, but I hope I can give a flavor for some of the elements involved by inviting you on a quick tour of some of the recent major discoveries in astronomy. So let's have a look. At major discoveries in astronomy over a really short period in time, from 1993 to 2005. And just to make it somewhat quantitative, let's just restrict ourselves to some of the discoveries that have won major prizes. We'll see that, well, the solar system was there was a lot more to it than we thought we discovered in this time period. We found that the solar system doesn't end at Pluto, but that it retains a small reservoir of very pristine, very primordial planetesimals that have valuable clues to our origins and to planet formation in general. We also found that in the same time period, that the solar system has a lot more planets than we thought, many planets like Pluto, and showing that planets are more diverse and more abundant than we could have imagined in the solar system. In the same time period, exoplanets were discovered. We've discussed a lot of that today. And although this discovery was made really only 25 years ago or so, and it really was a major step forward in our ability to think about the question of whether we're alone in the universe. Another major discovery in the same time period was of a supermassive black hole at the galactic center, where astronomers looked closely at the orbits of stars close to the galactic center and found that they could only be explained by a very massive, very dark object, confirming that our expectation that such objects would exist. Also, the final example is that of the discovery of dark energy, which showed that the universe is made is more complex than we thought, and how little we really understand, because everything about us, ourselves, our pets, our food, gas and dust and protoplanetary disks, all of that makes up only a small portion of the universe, something like 5%. And even before dark energy was discovered, we knew that that portion was quite small because there was another thing called dark matter, which interacts gravitationally, but we didn't know what it was. The discovery of dark energy shows that what we understand is even less than what we thought, because it makes up a very large fraction of the universe. So all of these discoveries, astronomical discoveries like these, provide us with some perspective. What kind of universe we live in, what's in it, how we got here, and how we fit in, our place in the universe. But let's look at what it took to make these discoveries. So here, this table summarizes the topics we've just toured, the kinds of teams or groups that made the discovery, and the kinds of resources that were used in the process. We see that the first two examples of the black hole at the galactic center and dark energy were made by teams of astronomers, sometimes working with the most complex resources we have available today, other times working with a wide variety of resources from very simple ones to very complex. But the first three discoveries were actually made by very small groups of people working initially with very modest resources. So what does this say? What can we extract from that? I think it shows that astronomy, although it's one of the oldest sciences, it's also a very youthful science, with discoveries made often and in diverse ways. Today in science, it's often thought that large teams are critical to the progress of science, to discovery, and sometimes that discoveries can only be made through large teamwork. But our own data, our own history shows that many major discoveries are made by small groups or individuals. Also, if you listen to the news or you read planning documents, you may have the impression that progress in astronomy and major discoveries can only come from state-of-the-art resources, the biggest, most expensive machines we can make. And you might be concerned because the cost of those machines is getting more expensive every day. But our own data, our own history shows that it's possible to make major discoveries with very modest resources. Perhaps those that are made available to groups with novel ideas or passions, who are willing to take big risks with recognizing the potential for big rewards. And while much of discovery technology does play a role, there are also very human elements that enter into the discovery process. The curiosity and passion that we bring to exploration and discovery, our novel and diverse ideas and opinions, and sometimes just very human elements like very extreme persistence. So that leaves me with, getting to the conclusion, that leaves me thinking that we have a very bright future ahead of us. The great diversity of pathways to discovery in astronomy gives us a lot of flexibility in our ability to respond to new challenges. And so I think that it's very likely that we'll be able to continue to contribute to society by contributing perspective on where we've come from, where we're going, and how we fit in. Where we really can't compromise, though, is on people and opportunity, because it's critical to be able to afford people with the opportunity, people with different ideas, outlooks, and skills, the opportunities to join in the discovery enterprise, because in fact, that's where many discoveries come from. So along those lines of opportunity, new challenges, and continued discovery, I wanted to thank the Radcliffe Institute for funding the Research Partners Program. Through this program this year, I have the privilege to work with two amazing groups of students. One group, Josh and Gabriel, branching out in a new research direction to explore the Milky Way using an exciting new data set. And with London and Andres, exploring an important issue facing science and society. I want to thank all these students for their great enthusiasm and insights, which are so inspiring to me. And I hope that gives you a sense of, in addition to the other topics that I discussed, I'll also be thinking about these topics during the fellowship year, and I look forward to your thoughts and questions. And with that, back to you, Claudia.
Thank you, Joan. This was absolutely wonderful. We do have questions, and the first one is, do you have a favorite solar systems or planetary formation disks? And if so, why?
Let me think now. I have so many. In thinking about one of the things that I work on, in addition to planet formation, is star formation, and these disks also play an important role in how stars form. And when you do this kind of work, or at least my favorite kind of work, is a really deep dive into really understanding individual objects and to see what kinds of clues you can really get. And so when you do that work, you really get to know each one in great detail. You have to know it very well in order to pull out new insights. So some of my favorites, one of my recent favorites is a class 1, a very young disk in the Taurus molecular cloud, in the Taurus constellation, called GV Tau. It probably means nothing, but it is a recent favorite of mine, and I've really been delving into that a lot.
Great, thank you. The second question is, what controls the size of the dust disk? Can it be gravity of a star?
Sure, that's a great question. There are so many things that enter into this. One of the major things is something called angular momentum. So a star and a planetary system forms from a molecular cloud, a much bigger structure of gas and dust, and it has some rotation. And so when it collapses, just like how a skater, when they pull in their arms, they end up spinning up. And so the material that falls down into the disk can't really fall right onto the star because it has too much angular momentum. It spins up too much. So that amount, depending on how much material, how much angular momentum the star and disk inherits, sort of dictates the size of the disk. That's overall. But the dust in the disk can act, and so that is really governing the gas part of the disk. What exactly the dust looks like is an additional set of considerations about how the dust and gas interact. And one of the recent discoveries in the last few years is that dust disks can be a lot smaller than their gas disks. So there are many, many factors that enter into that. And those processes all enter in figuring out where planets form.
Yeah, you are. So you say the gaps between rings might be planets. Are there other factors that produce such gaps?
Oh, yes, that is an excellent question. There are, as soon as these rings and gaps were formed, of course, we thought planets because that's kind of what we had expected to. If you're thinking planets, you expected to see rings and gaps, and then when you see them, you think, planets. But there are so many other things that you want to explore and rule out before you can really be sure. And there are, as it turns out, there are many processes that could produce these kinds of structures. So in the literature today, there are a lot of different ideas that people have. And part of the challenge is to figure out what are the specific predictions for the patterns that we would expect to see, and how can we distinguish among them in order to determine whether they're planets or not. A more direct method is to try to find the planets that are forming, because that would pretty much clinch it. And so a lot of work is going into that part as well. So yes, there are many other ways to produce these rings and gaps. So by themselves, they aren't definitive evidence. And astronomers are investigating various different kinds of ways to figure out whether they really are footprints of planets and what kind.
Mm-hmm. The next question asks, can you talk more about how you see the weirdness of our own solar system in the background of other planets around the universe? And then I'll read the second part of the question later.
Sure. So if we go back to our plot, you may remember that the solar system seems different from all the others because most of the other planets that have been discovered are much closer, and then from the rings and gaps, some are much more distant. But one thing I didn't have time to discuss is that finding solar systems like ours is still pretty challenging. Part of the reason why in our plot there were very few planets near the solar system could be that we don't have the sensitivity to detect those kinds of planets yet. They're much fainter, making them harder to see. They're smaller and more distant. So for all those reasons, we're really looking forward to upcoming space missions and ground-based capabilities, which should really help to fill in that space. So while the solar system still remains kind of unusual today, we'll have to come back in a couple of years to see whether that's still the case.
Right. So the next part of the question was, when you build your models, focusing on the non-Las Vegas-like smaller disks, do you come up with sets of planets that look like our solar system?
Oh, that's a great question. I'd have to really think about that. We didn't really, in the project that I did with working on with Scott Kenyon and Ben Bromley, we were really focused on trying to understand, what the rings and gaps were telling us. But clearly, this question is very perceptive, and that the next step would be to see whether the structures that are produced, the kinds of objects that form in these smaller disks really do end up like the solar system. That is actually people have come at that question from a separate issue of how to form the solar system in general. So it's not like that hasn't ever been discussed, but thinking about it the other way, from these observations and what new information do they provide about how the solar system forms in detail is a fascinating question. And thank you for that. And I'll be thinking about that later today.
Yeah, and there is another question about formation of planets. Can telescopes capture the moment when planets collide to form a bigger structure? Can they capture?
Okay, so we were discussing how to, if you're building Earths, you have to collide a bunch of Marses together. Can you see that process? The actual time it takes for the collision to occur is very short. So capturing the actual collision would be difficult, but the time it takes for the debris to be produced and to see that is much longer lived. So I think astronomers, we generally we can't look at every star all the time at the exact right wavelength to capture everything that's happening. So our favorite methods to detect those sorts of things are to detect long-lived structures. Mm-hmm. But it may be possible to detect changes where, at one point you didn't see a lot of debris, but at a later epoch, maybe not right away, but that you do. So, and those kinds of changes have sort of been reported. So I think that opens up another interesting question, that as we have more data over time to possibly look for the kinds of changes that could have indicated these really big impacts. Good question.
So we're going back to the personal a little bit. So we learned from your bio why you were attracted by astronomy, and we were wondering here, What drew you to planet formation specifically?
That's a great question. So when I was a high school student, in Hawaii, in Honolulu, I don't really think I thought about like what I wanted to do in life, or even what careers were possible. You just know, it's like, I've been to the doctor, I've been in school, there's doctor, teacher, how many other ideas do you have? So it was really a revelation to meet an astronomer and see that that was a career. And I was just inspired by the beauty of what Jupiter looks like when you go close up. So that's always been something very interesting. And then when I was a grad student, I was working on something totally different. But it turned out that the thing I was working on, these disks, very close to their central stars, is also the same kind of distances where the first planets were discovered. So it just happened that something I was working on was closely related to the discovery of exoplanets. And so I've been working on it ever since, and it's just been a really fun ride.
Yeah, fascinating. The next question is, can you talk about the integration of theory and observation in your Radcliffe project? How does one step back from the assumptions that are baked into the field so you can make new discoveries?
Yes, that is a really good point. I think when you're doing a lot of very detailed work, it's very reassuring and tempting to go as far as you can with your assumptions, of course. And then, as you say, it's difficult sometimes to remind yourself that those are still assumptions. So I guess in my own strategy, which is just my own preference, really, but I enjoy working with others who have different perspectives and skills, and not staying in one field too long, because sometimes if I do that, I feel it gets a little stale. Like my ideas may become, I'm not being as creative as I could. So that's part of the incentive to move on to other things. Because as you mentioned in the bio, Claudia, I've done a lot of different things, and the kind of work that I described today is really a departure from much of my previous work. And as part of the fellowship program, I'm hoping to also think about some new directions as well. So maybe the answer to the question is to try to be aware of what assumptions you're making, and maybe not linger too long in the same field, at least for me.
Yeah. The next question asks, so one of the things about our solar system that has always struck me as odd is that we have small to medium mass planets close to the sun, then a couple of giants, then small ones again. We might expect that the sizes and distances would be more regular, but maybe there is more going on?
Great question. That's exactly the kind of pattern curiosity that guides a lot of what we do, because astronomy is not a lab science. You can't design an experiment to test your ideas, so you just have to work with what's out there. And much of what's out there are those sorts of patterns. So actually, it's kind of a basic thing of the core accretion theory that there's a special prominence for Jupiter and Saturn as sort of inner giant planets. And because they're so large, it's a challenge to make those things. And I think people have noticed, in the way the theory was constructed originally, that the sort of like the dividing line between the terrestrial planets and the giant planets is the distance at which water would condense into solid form. And if we think of water ice as being extra fuel for planet formation, you add it to your solid budget. You have your silicates and carbonaceous solids, but then you add a lot of water ice, which is a significant amount, and that can fuel a lot of planet formation. So the fact that water condenses very close to the dividing line between terrestrial planets and giant planets is one of the clues that we have to the importance of the so-called snow line in fueling planet formation. So we think that close to the snow line at several AU distances where Jupiter is, I meant several Earth-Sun distances where Jupiter is where we would get a lot of planet formation activity. So explaining why Jupiter is where it is. And that's also why people think that's really where a lot of the giant planets, exoplanets form, and that they migrate in closer to their stars. So great question. And that pattern is sort of what has been used to guide our thinking.
There you are. Great, thank you. The next question asks, could you say more about how your work relates to the question of the formation of life, which is a topic that came up in the abstract of your talk? Is there a relationship between the evolution of solar systems and planets and the evolution of life?
Great question. So I guess there are a couple of different ways to address that question, and I'm far from an expert on this topic. But clearly, if we think of life as being something that's like on Earth, the first step is to make an Earth-like planet. So that's one of the directions of what I talked about, whether we really understand how planets like Earth form, and whether they're as abundant as we think they are based on the observations. The other question, though, is if you think about it from an astrobiological sense, like where did the chemical ingredients of life come from? Were they the initial molecules, and were they synthesized on the Earth, or were they delivered from beyond the Earth? Those are really important questions as well. One of the things that astronomers like to do is try to figure out what are the conditions in planet formation environments to figure out what kinds of molecules could have been synthesized and preserved there. So that was a sort of the general idea of what are the conditions in planet formation environments that sort of motivated much of the work that I did previously, or still do, on the gas and dust in the planet formation region of disks. We're still far from having a real theory for how that all works, but I guess the kinds of work that I did helped to show that you can actually study that region and get some quantitative information out. But we have a long way to go, but there are many exciting research facilities that are being developed to pursue those kinds of ideas.
That's great. You've discussed plotting the distance and size of planets. Might one also plot the types of rings and the information you have about them in order to gain a better sense of the location of similar solar system to ours?
Yes, definitely. So instead of plotting planet mass as a function of distance, we could have plotted different kinds of things about rings as a function of distance. In the second plot that I showed that was planet mass versus distance, and it had the colored points that showed where the more distant planets were expected to be. That was kind of where astronomers had already taken the gaps in rings and tried to convert those into what planets they might be indicating. So perhaps that addresses a little bit of what you were thinking. But if you were to say, what could I infer from making a plot with where the rings are located? That's in fact one of the clues that we have to whether those rings are due to planets or not, because astronomers have looked for patterns of those rings. For example, whether they have anything to do with the water snow line or other snow lines, because those are expected at particular distances from their central stars. And if they all lined up with our expectations for where these snow lines would be, that would seem kind of weird that they would be planets when we could explain them another way. So indeed, the location of the rings are the kinds of clues that we use. And as I mentioned earlier, trying to figure out what they're actually saying is one of the big questions today.
Mm-hmm. The next, we can't escape talking about the moons here. So how similar is formation of the systems of moons around planets to formation of solar systems?
Great question. So for example, if we think of the moons around Jupiter, the Galilean moons, they are in a pretty compact configuration. suggesting that they could have an origin that's kind of like the planets around the sun. So just taking the model and make it smaller. And indeed, when planets form, one expectation is that the material that's creating them may have too much angular momentum, again, just to make a planet. And so planets may be born with circumplanetary disks, so little disks around the planets. And that material can be converted into moons. So that's the hypothesis. And one of the signposts, in fact, of forming planets, like in these rings that people have detected, is one idea is to look for those circumplanetary disks because they're much bigger than the planet themselves. And so potentially that is a signpost also of a forming giant planet. So all these ideas are great ones. Astronomers are actively using all of them in order to figure out what we're seeing.
Perfect. So going back to the last portion of your talk, the next question is, I'm surprised to hear that team science is not the only path to discovery today. Can you say more about the roles of large and small teams in research? And I would add what data they use. Can they use the data from the telescopes that you professionals use?
That's a good question. Okay, so on the second topic of whether data that professionals use are available for others to use, that is a hot topic in astronomy today. We are making every attempt to make our data reusable, recyclable, so that they can be used by more than the original group of proposers. And so that's in part why when I invited the audience to have a look at www.legacysurvey.org, that's the kind of place where you can look at all the same data that astronomers look at. And there are many other examples for people who are interested. In terms of large and small teams, as I mentioned, it's not that one group makes the discoveries only, but as it turns out, there was a wonderful paper that was published in Nature a couple years ago by Wu, Wang, and Evans that used citation statistics to illustrate how the action of large teams and small individuals and groups differs. And they showed that when you look at citation statistics, large teams are the best at developing ideas, making progress, advancing the ideas we have. But it's the smaller groups that really are the ones that make the most disruptive discoveries. So in that discovery ecosystem, we need to have both kinds of things going on. We need to support small groups that make disruptive discoveries and the large teams that can perhaps best advance them. So that's one of the concerns that I have today, that if we get out of balance on that, then that's not the most optimal. So.
Right. We have one last question, briefly. I'm mostly aware of astronomy through the Mauna Kea protest by indigenous Hawaiians. What are your thoughts on these protests?
That's a great question. And that was a topic of one of the research partners project that I'm doing with Andres in London. And as someone who's from Hawaii and very sympathetic to the protest, and also an astronomer, it's something in my mind to how to reconcile those two views. On the one hand, we want to continue the discoveries that astronomers have been making. That's part of my job at NOI Lab. But also, we have to do that in a way that is respectful and cognizant of the history that's come before. So I think actually that's where the flexibility comes in, because of the diversity and possible discovery pathways. There's not only one approach, one facility, one thing that's critical to discovery. We have a lot of flexibility in how we do that enterprise. And so I hope that's part of the equation in figuring out how to meet our commitments to society.
Great. Thank you, Joan. Thank you for your brilliant presentation and perspectives. I also want to thank you, the audience, for the terrific questions. I hope you'll be able to join us for our Radcliffe virtual programs. You can find out about future programs and watch videos of past events at radcliffe.harvard.edu. Thank you again for joining us today and have a good rest of the day. Bye-bye.